So we're going to keep going with our top-down look at the brain in terms of complexity, right? So the top of the brain is the cerebrum, and that is the human part. That is that very developed part in humans, which allows us to do things like problem solve, plan. That's also where we have all of our different lobes of the brain, the frontal lobe, parietal lobe. And then we get just deep to that, we're going to get to our basal ganglia and diencephalon, which is going to be that middle portion of the brain, which is going to be the animal brain, that mammal brain. And that's the part of the brain, like we said, that deals with things like emotions and memory. And then finally, we're going to get to that reptile part of the brain, which is that bottom part of the brain, the least evolved portion of the brain, you could call it. And this part of the brain is really responsible for keeping you alive. And it's shared essentially by all animals. So that's why it's called the reptile brain. This is the part of the brain which includes the cerebellum and then the brainstem. So we're going to talk about the brainstem first, and then we're going to finish with the cerebellum. So what's going on with the brainstem? The brainstem is really going to be the bridge between your brain and your spinal cord. Now, I said this before. We started with the spinal cord. The spinal cord really is an extension of the brain. So it's a separate, anatomical feature, but it's really part of the brain in the sense that it's all connected to each other. The axons that leave the brain from the cortex travel down the spinal cord. So it's all interconnected. But this is what connects the brain to the spinal cord. And it's really divided into three main regions. You have the midbrain, which is really essentially right in the middle of the brain. And it's the top portion, or the most superior portion of the brainstem. And then just inferior to that, we have our pons, which is identifiable because it has this portion that bulges out on the anterior surface. So when you look at it, if you see it, you'll see it actually bulges out here past the medulla and the midbrain. And then finally, the most inferior portion of the spinal cord is the medulla oblongata, and at the base of that is going to be what we consider the top of the spinal cord, where it exits the foramen magnum. Now, the medulla is also a feature that we mentioned earlier. That is where our nerve tracts cross over to the opposite side of the body. So the right side of the brain, at the medulla, it's going to cross over to the left side of the spinal cord, and then vice versa on the way back up. So we're going to take a look at each one of these regions, and then we're going to finish up. I probably will break this into 2 lectures because there's still a little bit left to cover. Okay, let's start with the midbrain. And the midbrain is really this portion right here, just superior to the pons. So the pons, like I said, has this area that bulges out on the anterior surface, but the midbrain is going to be this portion right here, also including this portion to the back, which I'm going to talk about in a moment. So first of all, it's the shortest section, and it has a couple different jobs. The first job is really it just relays information from the lower parts of the brainstem up to the cerebrum and the spinal cord. So think of it as just a place where neurons pass through. So it's not really doing anything in that sense. It's really, think of it as a road. It's a path down to the spinal cord and up to the cerebrum and the higher parts of the brain. But then it also has this special feature, which I want to focus on for a minute here, which is called the corpora quadrigemina. It's a mouthful, but the corpora quadrigemina is made up of, it's called the quadrigemina, quad means 4, because it actually has 4 components. There's 2 portions which are called the superior colliculus, and then there's 2 portions which are called the inferior colliculus. And those 4 portions together make up the corpora quadrigemina. Humans have a very underdeveloped corpora quadrigemina, and the reason why is because we are not prey animals. So I'm going to talk about this for a minute here. What does this structure of the brain do? Well, if you were sitting there right now and you're looking straight ahead at me talking, if you were to hear something, let's say there was a bang to the right, you're going to go like this, and you're going to look. Your head and your eyes are going to go together. Automatically, if your eyes are looking forward, they move with your head. And you might be saying, well, yeah, of course they do, Mr. Adolph. That's what happens. Well, this is why that happens. And I can show you these are hardwired together. I want everybody to look straight at me right now. Now, keep your eyes forward and turn your head. You can do it, but it feels kind of weird. That's because you're breaking the natural pattern. Normally, when you turn your head, your eyes just go with it. And that's a product of this part of the brain. That's not all it does. Its job is it basically connects sound to vision. And it allows you to be able to react if you hear something coming. So why don't we have very well-developed corpora quadrigemina? Like I said, we are not prey animals. We are predators, really. So predators have their eyes on the front of their head. That's how you can tell prey versus a predator. A prey animal usually has its eyes on the side of the head so it can see if something's coming after it. So something like, for example, the sheep brain that we would normally dissect in class, sheep have a very large corpora quadrigemina. It's a big section of that brain in that area, which makes sense because they have to always be looking out for wolves and other prey animals that are coming to get them. So This is just a structure of the brain that allows you to avoid predation, essentially. You know, you can use it for other things too, obviously, because if you're a predator, I should say, if you hear prey, it'll cause you to turn your head and catch it in time. So that's the main portion of the midbrain that we're going to focus on for this class. That it has a relay station for neurons going north and south, and then it has this corpora quadrigemina, which allows our eyes and our sound, essentially, our interpretation of sound. When you turn your head, you're going to go to the sound. Your head turns and your eyes go with it. Okay, let's keep moving. The pons really is this rounded, bulged portion that is going to be right here in the middle of the brainstem. And what is its job? Well, it actually, you know, it's a relay station, but it does something kind of cool. So we're going to talk more about the cerebellum at the end of this section. And just a little teaser, a little spoiler alert here. The cerebellum's job is it stores complex movement. So and I'll talk more about this when we get to that. If I learn, let's say, how to play a song on guitar, certain hand movements are required for that. And if I play them enough, I don't have to think about it. So if you tell me to play like Oasis or something, I could just play that song without thinking about it too much because I've done it so many times. This is where they store that. A better example probably would be like an athlete. If you learn how to throw a football, you don't have to think about it every single time. Even something as simple as driving or tying your shoes, you don't have to think about those things because that information is stored in the cerebellum. It does other stuff too. But how does it get that information? Well, essentially, when information from your motor cortex gets sent down the spinal cord to the muscles, what happens is a copy of it, essentially, gets sent to the cerebellum through the pons. So the pons, essentially, so if I want to make a motion, like, you know, if I do something, I know that's a very impressive motion. What happens is the motor cortex is going to send the information to my muscles to make me do that cool move. And at the same time it passes through here, the pons is going to send that information to the cerebellum. And it's going to get stored there. So it's pretty cool, actually, how it works. But that's really all it does. So it doesn't have any functionality, the pons, other than communicating between the cerebrum and the cerebellum, which is very important. So if the pons isn't functioning correctly, you're going to see people with really hard time with simple movements, and you know, people that have issues with muscle contractions and things like that. And then the final part of the brainstem is the medulla oblongata. And the medulla oblongata is the most inferior portion, right where the beginning of the brainstem is. I'm sorry, where the spinal cord is. So it's a large continuation of the spinal cord, and this is where all those neurons cross over, like I said. So this is that kind of like, think of it as a crossover station where the nerve tracks cross over from the right side to the left side, from the left side to the right side. And that is going up and down. Remember, your nerve tracks, your ascending tracks, which are sensory information, are going to cross over, and your descending tracks, which are motor information, are also going to cross over. So that's an important feature. But there's also another very important feature of the medulla. The medulla is actually the part of your brain which is keeping you alive in terms of your heart beating, your blood vessels dilating, and breathing. So it has these things that are called control centers, and there's specific areas of the brainstem which control different vital functions, and then there's also non-vital centers. So I'll explain that really quick. So the three main centers of the medulla oblongata are the cardiac center, the vasomotor center, and the respiratory center. The cardiac center is what's going to control your heart rate. The vasomotor is, vaso means blood vessels and motor means movement. So these are going to cause the constriction and dilation. So when your blood vessels dilate and constrict, that's going to be caused by this center of the medulla. And then finally, your respiratory is going to be your breathing. So it controls your breathing rate. Now you can hold your breath. You can override that with your motor cortex. But if you don't think about it, you're going to go back to breathing your regular breathing. And then if you were to increase your activity level, this would be the thing, this would be the part of your brain which triggers your both your heart rate and your breathing rate to go up, so you have enough oxygen to get to your cells so they can function. And then finally, the non-vital section of the medulla. These also, this part of the brain also controls these things like coughing, sneezing, swallowing, vomiting. Yeah, it's kind of gross, but those are things you can't control. They just happen, and this is what causes them to happen. If you were to breathe something in that was like dust, this would trigger your medulla to cause you to sneeze, and then you would get rid of it. We're going to finish up with the last concept in this lecture, and then I'll do a very short one to finish up. I just don't want to go through too much in one lecture. I want to talk about this thing called the reticular formation. And the reticular formation is an important part of the brain, and it's something that you can probably all relate to because you've experienced when your reticular formation stops doing what it's supposed to do. Okay, so what is it? So first of all, where is it? It's not in a distinct area. The reticular formation is scattered throughout the entire brainstem. So if you look at this diagram here, the reticular formation is this pink area. So there's just neurons that are basically going to be scattered through this area. So you're going to find them in the midbrain, the pons, and the medulla. So it's not a distinct region. And what do? Well, essentially what ends up happening is this is the part of the brain that wakes up your cerebrum. Your cerebrum is the thinking part of your brain. When you stop activating it, you fall asleep. That's what happens. So it's like shutting down your computer. So the reticular formation is what keeps your brain awake, essentially. It keeps your cerebrum turned on. And when it gets deactivated, your cerebrum shuts off and you fall asleep. That's what happens when somebody goes into a coma. So when somebody's in a coma, there's damage to their reticular formation. And that's why they sometimes put people into what we call a medically induced coma, right? So sometimes people have a situation where they have, let's say, swelling of the brain, and they can't be awake for it. It's too dangerous for them to be awake, and they want to make sure this patient is not going to ever, move and move around or do anything like that. They could actually inhibit the reticular formation through medically induced comas, and that person will stay in a coma state until then it goes away. If it gets destroyed, that person will stay in a coma indefinitely. So that's how you can have a situation where somebody comes out of a coma. If it's caused by inflammation, so let's say there's damage to the brain, and it's not permanent damage, but it puts somebody into a coma. If there's inflammation of this part of the brain, it will inhibit those neurons from firing off, and that person will be in this coma state. But if that inflammation eventually goes down, if that trauma heals, that person will eventually wake up again. So it's pretty cool how that happens. Now, what's the point of your reticular formation? Well, what it does is, like I said, it activates your cerebrum, and it determines when you should be awake and paying attention and when you should not. It's why you set an alarm in the morning. How many people here in this Zoom, watching me, could sleep through an alarm? Some of you can, right? That's why it's good to change up your alarm. And the reason why is your brain determines whether or not something is a risk. So basically, perfect example. When I first moved to Philadelphia, I lived in a house with a bunch of guys. And we lived on a street corner, and we kind of drew straws for who gets to pick bedrooms. And I got one of the first choices. So I picked the front bedroom with the front windows because I was like, I want to have windows. I want to be able to look out. And it sounded like a great idea at the time until that first night. I didn't think about this. Well, there's trolley tracks out front, and the trolley tracks turn at that point. And if you've never heard a trolley turning on tracks, it is the most horrid, screaming, squealing sound. It sounds like shredding metal upon metal. And I didn't sleep that night because all night long trolleys were going by. And I was like, oh, I'm never going to fall asleep again. This is brutal. But what I found was after about a week, I started sleeping without a problem. It's not that I didn't hear that anymore. It's not that it wasn't still loud, but my brain determined that that was not a threat, so it ignored it. And that's the reticular formation that does that. And that is why when I teach in person, not in Zoom, but in person, I talk like this a lot, and I make my voice go down, and I do a lot of like weird stuff with my voice. And my students probably think I'm crazy, but I do it on purpose because what that does is it forces you to your attention back. Think about the teachers you have that talk like this, and they don't change their voice at all. They just talk like this the entire period. In a matter of minutes, everybody's like this because their brain figures out that that person's not a threat, and the reticular formation says, go to sleep, you're fine, don't worry about it. So that's why it's good to vary your levels if you're talking. But so that's what it does. The reticular formation is actually what is going to cause your brain to wake up. And this is what I'm going to finish up with here. It can go the other direction. Your cerebrum can actually activate the reticular formation. What is that? That's those situations when you're in those classes and you're falling asleep and you're like, no, don't fall asleep. And you keep kind of waking yourself up. That is your cerebrum activating your reticular formation, which is activating your cerebrum. So it's kind of hard to think of it that way, but that's really what's going on. So we're going to finish up here, and the idea, and I already said this, if that reticular formation is destroyed, that person's going to be in a coma. And they're in a coma for as long as that reticular formation is not functioning. Thank you very much.